Hey everyone, I'm Mohammed Gauss, and today I want to discuss about how we can model a naturally flowing oil well in Prosper software. So before going into the topic, I just want to discuss why it is really important to model any oil well or gas well. So just imagine you have discovered an oil well, and the data you have, it makes you excited about all the potential oil you can get from that well. But you are also wondering how to extract it efficiently from that well. This is where the well modeling comes in place. So by using real-time data like pressure, temperature, and the flow rate, and all the other data which we have collected at the time of exploration, with the help of these, we can create a virtual model of the well. So this helps us predict how the well will behave under different conditions. For example, by understanding the inflow performance relationship, that is even called IPR, we can see how much oil the reservoir can deliver at different pressures, and with vertical lift performance, we can get insights into how the fluids will move up the wellbore. So modeling an oil well not only helps us for optimizing production, but also it predicts the potential issues and also gives us the best operating conditions. It's like having a crystal ball that helps us avoid problems like gas lock or even hydrate formations. So in a nutshell, modeling an oil well helps us make smart decisions to get the most oil out safely and efficiently. So yeah, first things first, let me tell you what we are going to do in this modeling. So I will make you understand how to make a simple Prosper model, and then I will take you through the PVT data, IPR data, and equipment data. So from these all data, we are going to perform a system calculation, that is VL against, against the VLP versus IPR. So it will be helpful to estimate the well flow rate for a given wellhead flow pressure, and we can generate a well performance curve from that. So yeah, let's start. So here, if you can see, there is a option summary. So when you double click on that, here the pop out you can see. So here the main thing in this pop out is you want to select the fluid model, and here the fluid model was selected as oil and water. So the main reason why we are selecting this fluid model is, once we select this fluid model correctly, then the Prosper model, the this Prosper has designed, the way this Prosper has designed, it gives an accurate behavior of both oil and water. So making sure the fluid type is set right, it avoids any issues in your calculations later on. So that's why it becomes the most important to select the correct fluid model. So here there are different fluid models. When you are dealing with what type of well you are dealing, so it depends on that. So currently we are dealing with oil and water, so I had selected that, and all the remaining data was like pre-selected. If you can see the here method, which method it is, the Prosper is following, like is black oil method, and the separator, we just assume that it is a single stage separator which we are using in our group, and there are no emulsions. I'm assuming that there are no emulsions in downhole the well, and the hydrates, I had disabled the warning, as I am assured that there are no hydrate formed below the well, and the water viscosity, I have leave it as a default correlation it used, and viscosity model, it will be Newtonian fluid, and flow type of a well will be tubing flow. The production is through the tubing. So I had selected the tubing flow. It may be annular flow and it may be tubing plus annular flow. It depends on the type of production which is going on in our well, and the well type is should be the producer well. So I had selected it as the producer. The remaining all are the pre-selected data. So you can leave as it is. Here the main thing is was you have to select the fluid model. So once you have entered all these data, you can simply click on the done button. So yeah, here you have set up a basic Prosper model. So the second thing you want is you want to go to the PVT, you have to enter the PVT data. So for PVT data, you have to double click on this second box seeing here. So when you double click on it, you will have a pop-up like this. So in this, they are asking for the values of solution GOR, well, gravity, gas gravity, and water salinity. So simply I am giving some values which I have, like solution GOR will be 400 standard cubic feet per stock tank barrel, and the oil gravity will be 30 API, which is not so bad. It is good, and the gas gravity will be 0.75 specific gravity, and the water salinity will be 80,000 ppm. So yeah, here the correlations used by the Prosper software were Glasso correlation, and the for the oil viscosity it is B little. And here when you enter this gas oil ratio, it is very important you want to understand the GOR, what is actual GOR means. Actually this GOR tells us about how much gas is dissolved in the oil, and that affects that affects how we calculate that flow rates. So, and here the below oil gravity, it is simply the measured, it gives us the idea of how viscous the oil is. When you understand the API gravity formula, in that you can simply understand that how viscous the fluid, lower the API gravity value, viscous the fluid, and higher the API gravity value, more lighter the fluid, the crude oil was. So yeah, that's the simple formula. And once you enter these things, you can simply click on done. Once you have done, it is showing that we have to enter the equipment data. So for equipment data, you can see the option here below the option summary, the equipment data tab. So when you double click here, you can see different tabs, different options for the data to be entered. So I'm selecting all of these: deviation survey, surface equipment, downhole equipment, average heat capacities and all. So you can simply edit. So when you edit this, here the first option, first data to be entered is deviation survey. So as I'm dealing with a very simple vertical well, so at a measured depth of 0 feet, the true vertical depth will also will be the 0, and at a measured depth of 8,000, as there are no deviations and all, the true vertical depth will be also 8,000 feet. So once the deviation survey data was entered, just simply click on done, and you will can see the pop-up of surface equipment. But now I'm just skipping this surface equipment data. I'm going to enter the data for the downhole equipment. So in downhole equipment, I will be starting with the wellhead. So wellhead will be at the surface. So I'm just labeling it wellhead as a measured depth of 0 feet. And the second, I'm just considering very basic downhole equipments like only tubing and the casing. So for tubing, I'm here just placing. There are so many other downhole equipments. If they are in use in the well in real time, you can just enter those and you can simply model the well. So for tubing, it is up to the depth of 7,800 feet, and the tubing inside diameter is 3.992 inches, and the tubing inside roughness is 0.0018 inches, and the second download equipment will be the casing. I'm just labeling it, and it is to the depth of 8,000 feet, and casing inside diameter will be 8.3 inches, and casing inside roughness it will be 0.0018 inches. So after entering this data, you can just simply click on done, and once you click on done, here you are asked to enter the geothermal gradient data. So it is nothing but the change in temperature throughout the well, formation of the well. So here at the measured depth of 0, the formation temperature is 70 degrees Fahrenheit, and at a measured depth of 8,000, formation temperature is 200 degrees Fahrenheit. So overall heat transfer coefficient to from the 0 feet to 8,000 feet will be 8. So simply click on done, and the average heat capacities, I'm leaving it as it is, and I'm just simply clicking on done. So once you completed entering this data, you can simply click on the summary, and once you click on summary, you can simply click on this draw down hole. Yeah, here you can see a simple graphical representation of your well. You can see the casing part, the tubing part. It is all the data you have entered. It was simply mentioning that at the measured depth of 7,800 feet and the total vertical depth, and here also the same. So once you verified this graphical representation, you can simply click on finish, and you can click on here done, and good to go. You have completed the option summary, the PVT data, and the equipment data. Now it's time to enter the data for IPR. That is nothing but inflow performance relationship. It actually tells that how much amount of fluid will be coming or capable from the reservoir to the bottom hole of the well bore. So once you double click on IPR, here you have to select the reservoir model. So I'm simply clicking the Darcy model, and we have to enter the skin by hand, and the option we have to select, and the reservoir pressure here I am considering 4,000 psi, and the reservoir temperature as previously entered, it is 200 degrees Fahrenheit. And the water cut I am assuming as 0. It is nothing but the water percentage associated with the crude oil which we are going to produce, and the remaining I'm leaving as it is. And here once you enter this data, you can simply click on input data option. So in this input data, you have to enter the reservoir permeability, that is 150 millidarcy, and the reservoir thickness, which is going to be 100 feet, and the drainage area will be the 340 acres, and the died shape factor will be 31.6. The wellbore radius will be 0.354. So once you enter this, you have to enter mechanical skin factor. Skin factor is 2. Yes, you have done entering the data. Now you just simply click on the calculate option. So once you calculate it, you can see here the IPR inflow performance relationship graph. It is nothing but the graph against the pressure versus the flow rate per day. So here you can see at the pressure of 4,000 psi, you can have a production of 23,498 stock tank barrel per day. Here you can see the descriptive data. See, formation production will be 10.03 stock tank barrel per day, and the reservoir pressure is 4,000 psig. So we have done we have done plotting the IPR curve. Now it's time for the VLP. So we have done half a way from reservoir to bottom hole of the borehole, bore well. Next, we will simply click here done. And for VLP versus IPR matching, we just have to simply click on calculation, and then we have to go to system, IPR plus VLP, and we have to just click three variables. Once we click on the three variable, here I am considering the wellhead pressure, or we can say the top node pressure, to be 250 psi. So we can just continue here, and here also we can, for now we can skip these variables. Yes, here you can simply click on calculate. So once you completed the calculation, here you can see the solution details. So here just taking you through all these data. It is nothing but liquid rate. It is 10,898 stock tank barrel per day, and the gas rate is 4.3 million metric standard cubic feet per day, and the oil rate the same. The liquid rate 10,898 stock tank barrel per day, and the water rate is 0, as we have selected the water cut 0%. So solution node pressure is 2,641 psig, and the wellhead pressure is 250, and the wellhead temperature is 157. And here you can see all the remaining data. Let me show you this in the graphical presentation so you can better understand. So for that you have to click on plot, and you have to click on system plot. So yeah, here you can see a plot again, two curves. That is, one is IPR curve, the other one is VLP curve. So here you can see this interaction point. This interaction point is nothing but the bottom hole flowing pressure. So here you can see solution node pressure is 2641 psig. That means at this particular pressure and the top node pressure of 250, the production will be stable. Inflow IPR and VLP will be balanced, and there will be a stable production from the reservoir to the wellhead. So it simply tells us that from the reservoir, whatever the pressure, the oil was coming to the bottom hole of the well, and from the top from the top wellhead, whatever the pressure we are maintaining, that both are matching or not. Like here you can see the interaction point is at 2641. That means at this interaction point we can have a lift from the bottom hole, VLP, vertical lift performance. We can have a oil lift from bottom hole to the wellhead, or the crude oil, or any here simply the main crude oil. We can have a lift of crude oil from bottom hole to the top wellhead. So here you can see in this description, the liquid rate will be, yes, at this interaction point you can see the solution node pressure is 2641, but at this solution pressure or bottom hole flowing pressure, what will be the production rate? At this pressure, the production rate will be 10,898 stock tank barrel per day. For that also, when the solution node pressure has arrived, when we have maintained the top node pressure of 250 psig. So you have to mainly remember three things here: the wellhead pressure, the bottom hole flowing pressure, and the third one is the liquid rate, at what rate it was producing. When we have these both pressures, at what rate the liquid was producing. So here you have seen when we maintain the top node pressure of 250 psig, we are achieving a bottom hole flowing pressure of 2641, and we have a production rate of 10,898 stock tank barrel per day. At the same time, let us draw a performance curve, like you can see here at different pressures, at different, what if we uh, change the pressure at the wellhead, what if we drop the pressure at wellhead, what if we increase the pressure at wellhead, what will be the production rate, what will be the difference in the production rate. Let us draw that also. Let us have a look on that. For that, we have just simply click on done here, finish, done. And now you have to simply go to the main option. So once you go to the main option, let's come back again to the calculation. So in calculation, system IPR, three variables, continue. So yeah, now the variables part has come. So for that, what I have told, if we change the pressure at the wellhead, that is nothing but top node pressure. Just search for the top node pressure in this drop down, or the first node pressure simply. So first node pressure. So here I'm having a range from 50 psig to 1200 psig. So simply for I have generated, and the first value is 50, the last value was 1200, and for that I mean the range, I mean it was asking for the spacing. So here we can give a spacing of 10. So it will do in a linear spacing, give the gaps in linear spacing, and we can just generate. See, the values were generated automatically. Or you can simply clear data. You can, if you don't want those data in a linear format or what, you can simply just write 50, and the other one I want at 100 psi, and the other one was simply like 150 psi, another one was 200 psi, and that go on. And simply you can, I'm just writing the random, or in a simple format like 700 and 800, and the top is 200, right? So now I'm going to continue the same. So once I click on continue, let me click on the plot. I'm sorry, the calculate. Sorry, calculate. So you can see here at different pressures it is calculating. First node pressure 400, 700, 500, like that. Yes, the calculation has done. Now I simply draw a plot, system plot. Here you go. You can see what the green one which you are seeing was an IPR, and the red was a different VLPs. See, at here it was given the 50, 100 different knot pressures. So here you can see, like at 50 knot pressure, the oil rate was 12,283 stock tank barrel per day. Okay, and the solution knot pressure, that is nothing but the bottom hole flowing pressure, is 2,468 psi. Same you can check for the others, because in the plot it was not clearly visible. We can check here, and for the same 150 and the same 200. So like this you can estimate, you can uh, I mean optimize the ways, like you can give the better solutions at what pressures, at what pressure it will be the best to produce. And it is the very safer way to understand the production rates of any oil well. So yeah, that's all for today. I hope you like this video, and there are further more parts which are going to come in future. So Yeah, stay tuned, stay updated. Thank you.